company Mecwins develops sensing nanotechnologies for molecular diagnosis. Dr. Montserrat Calleja founded Mecwins in 2008, together with colleagues researchers at the Bionanomechanics Lab, CSIC.
We aim at simplifying the sophisticated analysis required by the personalized medicine approach in healthcare, and in order to do that, we need to develop new technologies and new instruments. The goal of Mecwins is to offer easy and accessible molecular diagnostic methods.
The company is pioneer in the development of nanomechanical sensors for personalized medicine. These devices consist on tiny membranes or beams that deform under the forces caused by molecular recognition events on their surface. Alternatively, the changes in the vibration of the beam can also be used as a signal to detect biomolecules and even to weigh them.
Nanomechanical sensors have several advantages for the development of new concepts in point-of-care devices. They can be easily miniaturized, they provide high sensitivity, and they need only of small sample volumes, so a single drop of blood could be enough to run a test. Also, we have patented a method to read out hundreds of sensors in a minute, so the measurements are fast.
Mecwins technology allows the fast scan of large surfaces while keeping a vertical resolution which excels 1 nanometer, allowing for the rapid readout of the response of hundreds of sensors.
What's most appealing with these nanobeams is that we have not yet seen their limits as sensing devices. With a cantilever-like structure a few hundreds of micrometers long, we can weigh single bacteria. But if we cut down the dimensions of the beam to that of silicon nanowires, which are only 100 or 50 nanometers in diameter, then we can weigh a single protein. We also try to understand the interplay of light with these small objects to be able to interpret the nanomechanical signals. This basic knowledge is relevant to the development of reliable biosensors. In the same way, by understanding how biomolecules change their conformation in the presence of water molecules, we have been able to develop novel DNA biosensors. This means the work to be done includes basic science in physics and chemistry, but also development of mathematical models to understand the nanomechanical deformations and translate them into biosensing signals. Also hardware and software development and engineering. And all of this effort has a final goal, and this is to provide better diagnostic tests.
Miniaturized devices can run advanced tests in moving healthcare units or even at the patient's home. As added advantages, they can lower the cost of sophisticated genetic and proteomic analysis, decrease the waiting times, and provide better informed treatment decisions to the patient in a very short time. Today, Mecwins technology for the readout of hundreds of nanomechanical sensors is being commercialized worldwide. The ultimate goal of the company is to launch a handheld device for the detection of clinically relevant proteins.
Scientists, we enjoy pushing the boundary that separates the known from the unknown. This effort, in order to advance basic knowledge, is stimulating and rewarding. But when this is combined with the consciousness that the answer questions could change our lives, it adds flavor and spices up our everyday work. I'm currently working at the Microelectronics Institute of Madrid, which belongs to CSIC, and we collaborate with Mecwins through technology transfer agreements and contracts. Now, I'm intensively working in a challenging frontier research project called Nano4Cells, funded by the ERC through a starting grant. One goal of the Nano4Cells project is to develop new instrumentation to measure physical properties of large numbers of single cells. We want to measure mass, density, elasticity, and refractive indices of the cells, because we believe this will help us understand why and how they become malignant. I see this project as the seed for future technologies that may change the way we approach to the diagnostic of diseases. Up to date, we use chemical biomarkers to aid in disease diagnosis, but in a near future, I foresee that physical biomarkers will be also helping to earlier, better, and faster diagnosis.